Hello, good evening. Can you hear me and can you see my screen? Hello, can you hear me? Can you hear me?
Yes, sir.
Okay. Okay, we'll start then. It's 10 past 7 already. So, this week also we'll be concentrating on problems of induction motor, three-phase induction motor. This is the 7th week of this course, Electrical Machine 2. It's taken by Professor T.K. Bhattacharya, and this is the Monday session, 7th week. So, as usual, I will start by asking doubts from your side. If you have any question from these or last week's lectures, I'll clarify, then we'll go ahead for solving the problems. Okay, so in today's class we will look in mostly into the energy flow of three-phase induction machine. So energy flow means some input power that comes into the stator. So this goes into the stator. Stator consists of two parts, winding and core. So there is loss associated in both the components, winding and core. The loss that happens in the winding is the copper loss. So that much energy, the stator copper loss, that is lost. And the loss associated with the core is the stator core loss. Now rest of the energy is for power, let us say power, air gap power, This goes to the rotor. This goes to the rotor. Again, rotor has two loss. Similarly, rotor copper loss and rotor core loss. Rest of the energy is the gross mechanical power, of which goes out the friction and windage loss. So here is the isolate. Okay, friction and windage loss. And what is available outside is the shaft power. Okay, so here is basically the isolation, or you can say here whatever, the air gap. So the first problem is based on these concepts only. So if there is no doubt, we'll start solving the problems. Today's problems are quite calculation extensive. So I hope that you can do vector calculation in your calculators. Vector, or basically complex calculation, not vector. Same thing. So complex calculation you are supposed to do by yourself in your calculators. I will not show those calculations here, directly use some solutions. We'll just discuss the processes. The first question is, consider a 8 kilowatt 3-phase 10 pole 450 volt 60 hertz star connected induction motor. Stator resistance per phase is this much. At no load, draws a line current of 8 ampere and input power of 680 watt. At full load, it draws a line current of 15 ampere and this much input power. Total friction and windage loss is this much. Rotor copper losses at no load is negligible. Estimate the stator core loss. Okay, so first let us find out the synchronous speed. Although we do not need it at this step, still it may be helpful. It gives some idea. Synchronous speed is 120 by p. Frequency 60. The synchronous speed 720 rpm. Now what is the stator core loss? So if we look from here, from this thing, now let me copy this image here. Just a minute. Yeah. So this is the flow of energy. Now it is saying that at no load, rotor copper loss we can neglect. So we will simply keep putting 0. No load, sorry, not no load. Yeah, no load. So rotor copper loss, they have said 0 at no load, and shaft power is 0. Shaft power is 0, no load. There is no mention or hint about rotor core loss, so we can neglect it here. Not mentioned anything. Now what else? Input power is known. Input power is 680 watt. 680 watt. What is the stator copper loss? Stator per phase resistance is given. It's a star connected induction motor. So whatever the line current, that much is the phase current. So copper loss is 3 times current squared resistance. This. Okay. This we have to find out how much. And so rest of the energy goes into the rotor, and in the rotor the only loss is friction and windage loss. So from here we can then write the equation that input power is the stator copper loss plus stator core loss, and it is a PC, plus friction windage loss, which is 200. So from here, if you find out, stator copper loss comes out to be 403.2 watt. Any doubt in this? Yeah. Okay, then go to the next question.
So
Yes.
rotor copper loss.
Rotor copper loss, they have asked us to neglect at no load. We did this problem taking this line current value at no load. The core loss, it's a function of frequency and flux density, which remains constant throughout the operation, because the frequency remains same in the stator, and since the voltage is also constant, frequency and voltage, hence the flux density is also constant. So the core loss is constant, doesn't matter whether it is full load or no load or whatever the loading condition might be. The core loss is same, so we can do it at any loading condition. Now since we do not have data of the rotor resistance and all, and we have been asked to neglect rotor copper loss at no load, it's easier to calculate this in no load. Rotor copper loss we need not consider here. The next question is estimate air gap power at full load. So as I said, the stator core loss remains the same, does not change. So at full load also, stator core loss does not change. So air gap power what all do we have in fact full load? A full load input power is given 9.2 kilowatt. So air gap power is simply from this diagram again. It's 9.2 kilowatt into power minus stator copper loss. Stator current is given as 15 ampere at full load. So 3 into this minus stator core loss. So this is the air gap power at full load, which is 8526.8 watt. Okay, the next question then. Rotor copper loss at full load. Let us see what do we have. Rotor copper loss. Okay, so this power we know. This power is known to us, the air gap power Pg, and friction windage is given to us. And see here, the machine is rated as 8 kilowatt. We discussed this in last class or maybe some other class, that if a motor is rated for 8 kilowatt, that means at full load it gives 8 kilowatt power. There is a shaft power available. So rotor copper loss is the air gap power minus rotor core loss is neglected throughout, no mention of it. Gap power minus friction minus shaft power. So shaft power is, okay, gap power minus output power minus friction. So gap power is, we found out 8526 minus output power is 8 kilowatt at full load, and friction loss is 200 watt. So this is the rotor copper loss. At full load. So basically this chart is this energy diagram or whatever you can call it. This is everything. Just apply law of energy conservation here. You'll get every data step by step. Now full load speed in RPM. This we discussed last day, that copper loss in rotor is slip times gap power. So slip comes out to be this. Both are known to us. 326.8 by gap power is the sleep comes out to be 3.8%. Now from here you already know the synchronous speed 720 rpm. We can find out, we know that sleep is omega s minus omega r parameterized. Which will give you this to be this much rpm. So this is the full load speed. So notice one thing here, this data is more or less realistic, quite realistic. The full load sleep is 3.8% only. So yes, 3.8%. That means when the induction motor is fully loaded, only a speed reduction of 3.8% is seen compared to the synchronous speed. No load speed is a little bit lower than the synchronous speed. So induction motor in its full operating range more or less operates at a constant speed. if the frequency is kept constant, supply frequency is kept constant, and voltage. Now, if this is clear, we'll go to the next question. Estimate gross mechanical torque developed at full load. Gross mechanical torque. So, the gross mechanical power is 1 minus S PG, gross mechanical power. This divided by omega R is the gross mechanical torque. Let me write TEM, electromechanical, electromagnetic. Now, omega R by 1 minus S is omega S. So what we are getting is PG 8526.8 by omega S. This should be in SI. This will give you gross mechanical torque. Now shaft torque. So from here you have to subtract the friction loss, that will give the shaft torque. So what is the net available power? Net available power is 1 minus SPG. This much is the gross mechanical power. This minus 200 watt. There is a friction loss they have mentioned. Or else we can do it the other way. We know that output is 8 kilowatt. You can do it in this way also. 1 minus SPG divided by, sorry, then total power developed by omega R, which is nothing but the output. Output is 8 kilowatt, we know. 8 kilowatt. And we have just calculated the full load speed, 692.4 RPM. So this is the 110.3. So this is what is developed by the motor, of which this much is available. This is the rated torque. Okay. Or sometime, as we mentioned, is also called the BHP, brake horsepower. Next part is estimate the efficiency at full load. So full load input power, output power are known. 8 kilowatt, 10 kilowatt. Output power is 8 kilowatt, input power is 9.2 kilowatt into 100%. Okay, so tell me if there is a doubt here. Okay, then we'll go to the next question. This is the one. Hit the question once. So the equivalent circuit is given. Above figure represents the per phase standstill equivalent circuit. Refer to the stator of a 3-phase 6-pole 500 volt 50 hertz star connected induction motor. So 50 hertz 6-pole is 1000 rpm. Synchronous speed. Total friction windage loss is given as 1600 rpm. Estimate the starting torque. Okay, so starting torque means the machine is still at standstill. So basically what you have to do is solve this circuit. Some voltage is here, some voltage is here, and then solve the circuit to find out how much current is flowing to the rotor circuit. So the per phase impedance is stator impedance plus, which is in series with the magnetizing branch and rotor impedance. So that is this in series with 2 in parallel, J80 parallel with this. So this is the per phase impedance at standstill. Now, if you solve this, if you simplify this, you will get 0.35 real part plus J 3.95 ohm. Okay. Now, what we have to find? We have to find out starting torque. Starting torque is anyway the mechanical. So in this we saw that torque electromagnetic, which is the gross torque, is 1 minus SPG by omega S. Sorry, omega R. Starting both omega R is 0, 1 minus S is 0. But actually omega R by 1 minus S gives you the omega S. So this can be written as this also. So if you can find out the gap power, that will be enough. So gap power is input power minus stator loss. So what is the input power? Total input power is root 3 VL IL cos phi. Now you have to find out IL first. How much current is flowing? It's a star connected motor. So phase current is equal to line current. So what you have to find out first is the line current. So IL is 500 volt line to line they have mentioned. Even if nothing is mentioned, it is line to line for three-phase system. Now this by 0.35 plus J 3.95 ampere. So this gives stator line current of 72.77 angle minus 84.90 degree ampere. Notice one thing here, the angle is almost 90 degree. So the starting power factor is very poor. Yes, starting power factor is very poor. Okay. So now IL is known, cos phi is known, √3 times line voltage 500 times IL cos this is the input power, and from input power we have to subtract the stator copper loss. 0.2 ohm is the resistance, so stator copper loss 3 times I squared. And notice here one thing, that whenever you are doing such problems, make sure that you are either doing it for the whole machine or either doing it for one phase. Do not mix it up. When I am writing √3 VLIL cos phi, that is for the whole machine, not for a phase. Now, since this is for a whole machine, in calculating the stator copper loss, I have to multiply a 3 here. 3 I squared times R 0.4 3 I squared R. So not 0.4, 0.2. Last one was 0.4. This. So the input power, and one more thing is they have not mentioned anything about stator core loss here. That's an experimental thing, and resistance and other things are not given. So one assumption that goes in this problem is core loss is neglected. No data or hint is there in the question about core loss. Okay. Now since that is neglected, the gap power is input power minus stator copper loss, which comes out to be this much, the gap power. Now we have got PG. So starting torque is PG by synchronous speed. Starting torque, also the stall torque. Stall means standstill condition. So starting torque is also stall torque. That is PG by synchronous speed, which is 2419.05 by 1000 RPM in SI unit. This gives us 23.1 Newton meter. So basically, if you draw the curve,
Excuse me, sir.
yes.
I think frequency is given 50 hertz.
I have taken 50 hertz only here, 120 f by p. This is not frequency. This
Yes, yes,
factor
yes.
is converting RPM to radian per second. So
Got it, sir.
if this is the torque speed curve, something like this, cannot draw it properly. So this is the synchronous speed where sleep is 0. This is starting where sleep is 1. Here the torque is 23.1 Newton meter. Okay. Estimate the line current at starting. Already did that here, 72.77 ampere. Estimate the slip in percentage at which maximum gross mechanical torque occurs. So we have to find out this speed or this slip we have to find out. Okay. Now if you see maximum gross mechanical torque, so torque electromagnetic, that is gap power by omega s, we already found. Now gap power is the total, if you remember last days, that this is how we can draw the rotor circuit where the frequency is constant. X2 here, 2 by S. So the current that flows I2. So the gap power PG, there is input power to the rotor circuit, is nothing but I2 squared R2 by S times 3. Right. So PG is 3 I2 squared R2 by S by omega S. Right. Now the maximum power occurs when this R2 by S sees the maximum energy dissipation. Sorry, the maximum torque occurs when the R2 by S sees the maximum energy dissipation. Not the maximum power, okay? The maximum torque. The torque is not changing linearly with speed. So maximum torque does not necessarily coincide with maximum power. Maximum torque happens when you have this energy, this R2 by S is dissipating the maximum possible energy. Now, if you look at the circuit, here is the R2 by S. So now the question is, what should be its value Everything else here is constant. What should be its value so that it dissipates the maximum power? So this becomes a maximum power transfer theorem. So you have to Thévenize the source impedance. If the source impedance equals the load impedance, we have maximum power dissipation in the load. So we have to Thévenize the load circuit, how it looks from here. Now if you call this R1, X1, XM, and X2, then Thevenizing means what? Thevenizing means you have to short circuit the voltage source and then find out the equivalent impedance. So it looks like this. So what is the ZTH? ZTH is R1 plus JX1. This combination in parallel with JXM plus JX2. Is it clear up to this?
Sir,
Yes.
so this is asking the maximum mechanical torque occurs.
Hmm.
So the gross, agar if I consider like maximum torque occurs at the maximum gross power.
No, this thing is power is torque times speed. Right. Now on this curve, suppose say the green one is the torque versus speed. Now suppose if I draw say speed versus speed, omega equals omega, if I draw, that will be a simple straight line. Now if you multiply this blue curve and this green curve, that multiplication peak will not occur here, it will occur somewhere else. You got my point?
My queries are like it is asking gross mechanical torque. That is 1 minus SPG.
1 minus SPG is the gross mechanical power.
Yes. Divided by WR or something.
WR. This is the gross mechanical torque.
Yes.
Now WR by 1 minus S. This is W S, synchronous speed.
Okay.
Thing is, you cannot have multiple variables. If you start doing the solution, say if you start doing the solution, just a minute. If you start doing the solution with this expression, here you have two variables, S is varying, WR is varying. So when you are differentiating, in such cases, it's not a partial full differentiation. So we have to make sure that there is only one variable. If I now express the torque as this, I have only one variable, S. And I have to make sure the maximum current flows through it. Okay. Now this Thevenin impedance is clear. We are Thevenizing the source circuit. So now if ZTH is this, then the circuit becomes this voltage becomes VTH. Voltage does no longer remains the same, Thevenin voltage, and ZTH. Now when you have R2 by S equal to modulus, the real part, not the real part, the modulus when you have this, then the maximum power transfer happens. Or in other words, then you get the maximum torque. This maximum power transfer happens, I said this is not the maximum power transfer to the source. You understand the flow here. We have written something, some expression we have derived here. From this expression we found out that if we find out in the equivalent circuit how much is the maximum possible power through R2 by S, at that situation we will have the maximum torque. Okay. So in this situation, so for that value of S, when this will happen, we shall get the maximum gross mechanical maximum torque. So now we'll simply put this expression R1, Jx1, everything is given here, 0.2 J2 J2 in parallel with JXM 80 plus JX2 J2. This modulus of this will give you 3.95 ohm. And how much is R2? R2 is 0.16. So 0.16 by S is this. So slip comes out to be 0.16 by 3.95, which is approximately 0.04, which is 4%. And this peak occurs at 0.04. S in this direction, 1 here, 0 here. We get the maximum gross mechanical torque. Now, how much is the maximum gross mechanical torque? We can do from here. Let us quickly draw the equivalent circuit when the maximum gross mechanical torque occurs, or maybe that is in terms of S equals 4%. When S equals 4%, what is the equivalent circuit? What was the values? 0.2 J2 80. Again J2 0.16. So this is the situation when the maximum gross torque is happening and the supply voltage is 500 volts. So per phase it is 500 by root 3 volt star connected machine. So we have to find out the torque. Now, such a similar problem we did at the very beginning, where we had to do this at standstill. Now, only thing is this value has changed. The whole exercise will remain the same. The value has only changed. So again, total per phase impedance is 0.2 plus J2, which is in series with the parallel combination of this and this. You should get a value of 3.95 plus J 4.13 ohm, right? So this much is the Z per phase. So the line current I, or the stator current, you can say I1, that is flowing is 500 by root 3 divided by 3 point is the vector 95 plus J 4.13, which comes out to be this. Now, before we proceed any further, let us compare these two values. The motor is now running at this speed. The speed has quite increased compared to the standstill, right? It's now only 4% away from the synchronous speed. So the starting current and power factor, if you see, it was 72 ampere and 85 degree. Now the current has reduced 50 ampere and power factor has improved. So this observation you keep in mind. The induction motor, when you start, it draws large current and the power factor is poor, and then the power factor keeps improving. Okay. Obviously it's linear. There is some place where it's the best power factor you will get. Okay. So now we'll go forward. The gross mechanics. So basically in this situation, how much is the torque? We can easily find out the air gap power. Let us see. What we can do is input power. We'll find out input power is root 3 line voltage, line current, sorry, another 0, power factor, somewhat, and the copper loss in stator is 3 times. See, I did a root 3 VLIL cos phi, that is for the whole machine. So for stator copper loss, I'm multiplying 3 so to get the loss of all 3 phases. Okay, so 50.46 squared times 0.2. So now if you find out the air gap power PG, that is PI minus this will give you what? Gap power. Now we found out that torque is air gap power by synchronous speed. Synchronous speed is 1000 rpm. This will give you this much. So this is the peak torque that you will get. So now if we draw this curve again, this one we got some 23 Newton meter, and this one some 274 Newton meter. Now remember one thing, that generally induction machines are never rated at this torque, because if you try to operate the induction machine at this torque, the current will be very high. The operating region of induction machine more or less remains constrained in this zone. That is why if you do an induction motor experiment in your laboratory and then find out the torque speed characteristic, you will get a drooping straight line. You're basically getting a magnified version of this segment of the torque speed curve. Okay. So next question, you can stop me if you have some question. Estimate the net power output or shaft power when the maximum gross mechanical torque occurs. So net power output we have to find out. So what is the rotor speed at this condition? The rotor speed at this condition is 1 minus s times omega s. S is 4%. So 0.96 times 1000, which is around 960 rpm. So the peak torque happens at 960 rpm. We have to find out how much is the power output. The power output is the gross power we have just found out. Did we find out? So power output is 1 minus s pg. Pg we found out. So 1 minus s pg minus friction loss. Friction loss is given, I think 1600 watt is given. So 1 minus s is 0.96 times pg is from this, you can still see it in the screen, 28692.2 minus friction loss 1600 watt. So this will give 25931.87. Oh, power output is asked. So this is the power output. You can do it in this way also. Since we know the speed at this point and torque at this point, this can also be found out as 273.9 times the torque times speed, 960 radian per second. This should also give this. Okay. Now the question that was asked some time back, we will face that one. Now estimate the slip at which gross mechanical power developed is maximum.
Sir,
Yes.
So this is the torque, that is a gross mechanical torque.
This is what we did in last three problems. Maximum gross mechanical torque. This is at this point when the torque is maximum. This does not necessarily mean the power is maximum.
No, my question is like the shaft power
Hmm.
is equal to the gross mechanical this
Power minus
273.
friction. Oh, understood. Yes, yes, yes.
Yeah, yeah.
It's
You have
it's
to calculate
coming
the
more, is it?
shaft torque.
Yes, true. Actually, what we have to do is this minus.
The both are not matching actually.
This is coming more, right?
Yes.
Yes, the power should be how much more is it? Is it this much more? 1600 more?
It is coming 27,535
So 1600 more.
almost.
Hmm. Sorry, this was the gross. So this much is the developed torque, sorry, developed power minus the friction. This I did not do. Sorry. 1600 is the loss, friction loss. Is it matching now?
One minute.
Hmm.
Minus 1600. Yes, sir.
Mhm.
It is matching now.
So be careful while doing these things. I goofed up here. It is gross and available. We did not find the available torque though. So this one actually, if you divide by 960 times 2 pi by 60, divide, you will get the maximum available torque. Torque. Okay. Now the next question is estimate the slip in percentage at which the gross mechanical power developed is maximum. So gross mechanical power this is 1 minus s pg. So this is 3 times I squared, I2 squared, R2 by S. There is a pg times 1 minus s. So So you have to find out at what condition this resistance is dissipating the maximum power. We'll draw the circuit again. This is it. So R2 by S we have split like this. R2 by S is R2, the actual rotor resistance, plus 1 minus S by S times R2. So basically whatever current, so whatever energy that is dissipated in this resistance in the equivalent circuit is actually the developed mechanical energy, right? This is the voltage V. So now again we have to Thévenize the circuit, but from here. From here we have to Thévenize the circuit. So what should the ZTH be? Again, imagine in your mind that the voltage source is short circuited. So it looks like this. We are Thevenizing in this direction. So it becomes R1 plus JX1 in parallel with JXM magnetizing branch, and this whole combination in series with the rotor resistance JX2 plus R2. Right? So if I now put the value, R1 is 0.2, X1 is 2, XM is 80, plus J2 plus R2 is 0.16. So for maximum power output, 1 minus S by S times R2, this should be equal to this modulus of this, which you will get 3.97 ohm. So 1 minus S by S times R2 is 0.16. This. So now if you simplify, what you will get is S is equal to 0.0388, that is 38, sorry, 3.88%. So you see the maximum torque we got at 4% slip here. Here we have slip equals 1. Here we have slip equals 0. So slip equals 0, synchronous speed, slip equals 1. So slip increases in this direction. We had 4% slip here, maximum torque. Now maximum power happens somewhere less than that, 3.8%. That is at a higher speed. It is happening at some higher speed. Maximum torque and maximum power do not coincide. Okay. So what was the question? Sleep at which gross mechanical power developed is maximum. So this is the answer. Now the next part is estimate maximum net mechanical power output or shaft power. So we have to find out how much power is being developed at this slip and then subtract 1600 watt. So the same exercise once again, we have done it before. Basically, we have to solve that equivalent circuit for one new value. R2 by S. Here S is 3 point. Let me write the values. This is J2. Okay, so you have to find out how much power is developed in this situation. We can just find out the current. So similar approach, per phase impedance 0.2 plus J2. So I'm not explaining it anymore, just writing things for you. And stop though. We have done this exercise twice today. The third time we are doing this. This will give you this much per phase impedance. Now from here, if you find out the current, phase current, which is same as line
Divided by
current.
0.038.
Oh, sorry. Yes. This will come. Solution is there. So stator current that you will get is supply voltage is 500 volt line voltage. So 3 divided by which comes out now. Again, if you compare the current value, see what we saw, that the speed has increased compared to the maximum torque situation. Speed has increased. So the current has even more reduced. It was how much? At maximum torque, the current was 50 ampere, 46 degree. Now it is 49 ampere, 40. So current has reduced and power factor has improved. Okay, and power also has improved. So much better situation we are now in. Anyway, so what is the input power? Same approach we are doing. Input power is √3 VL IL cos phi. Let us do air gap power directly. We have done it much. This minus the stator copper loss 3 times I squared times R. So the gap power that we are getting is How much did I get? 28667. What? Okay, gap power. Another question is net mechanical power output. So power output is 1 minus gap power minus friction loss. So 1 minus 0.0388 times 28667.78 minus 1600. So this is the output power, maximum output power, which is 25956.4. Sorry, what? So this is the maximum possible power available from the torque. So the maximum possible power and from the machine, sorry. So the maximum possible power and maximum possible torque, they occur at two different speeds. One does not imply the other. Okay. The last question of the day. Estimate the resistance to be added to the rotor per phase so that the maximum torque occurs at starting. So what happens when you add rotor resistance? So this question clearly indicates that the induction motor that we have been solving the problems on, that induction motor is a wound field induction motor, not a squirrel cage induction motor, because then only you can add resistance to the rotor. Now suppose this is the natural characteristic, torque speed. If you add rotor resistance, the slip at which the maximum torque occurs, Sm, reduces, but the maximum torque remains constant. Maximum torque remains constant. So here, in this direction, R2 increases. If you look at the equivalent circuit, this is what we already have. This we have added external. Otherwise, the whole thing remains the same. This part of the circuit remains the same. So what we have to do is, the question is, how much resistance is added so that the peak torque happens at starting, so that that is the characteristic becomes like this. Notice one thing, every torque, every curve matches at the same point. This is because the frequency of operation has not changed, so the synchronous speed has not changed. So what we did here, that R2, now R2, sorry, This is Rx by S. Because at standstill condition we had R2. Now with that Rex is being added. So the whole thing is now in the circuit. So the whole thing by S, Rx by S. So R2 plus R external by S, this should be equal to that ZTH. See, this ZTH component is not changing because others are same. So if we now go back to the maximum mechanical torque, so this ZTH. Okay. This we have brought from the maximum mechanical torque. There we got this 3.956 ohm. Okay. Now we want this maximum torque at starting. So at starting, what is the value of slip? Slip is 1. That is R2 plus Rx equals 3.956 ohm. R2 is given as how much? 0.16. So see 3.956 minus 0.16. How much is it? 3.796. So if we do this, we are getting this black characteristic as we should see here, so that the maximum torque occurs at the starting itself. And also notice one thing, this resistance is adding to the total circuit resistance. So it reduces the current. So it not only increases the starting torque, but also reduces the starting current. So that's all for today. Something I want to just tell you, that as I said, that the rotor copper loss is called the slip power. Slip power. And say for example here what we did is, with the rotor resistance in series we added another resistance. Slip power increased, but that is a loss. We are getting some advantage, but the energy is lost. The rotor or the machine does not understand whether the energy is lost in a resistance or goes somewhere else. What it can see is some power is being dissipated, some power is being absorbed in the rotor, which is not going to the mechanical side. So sometimes what is done is, say the rotor circuit is taken out through through slip rings, and instead of connecting resistances, see you can connect resistance like this. That will cause a loss, but instead of connecting resistance, what you can do is feed this power back to the grid. You have three-phase grid here. Feed this power back to the grid, so the machine will see that the power is being absorbed by rotor, but we are not losing the power. the power is being fed back to the grid. That's a win-win situation. But the only problem in this scheme is here the power is the frequency of the current is SF, whereas here the frequency is F. So you cannot directly connect these three wires to the grid. You have to match the frequency. So one way of doing that is first convert this to DC. Then you have a three-phase inverter. Inverters switching fundamental frequency will be at the grid frequency, and you connect it to the grid. This is sometimes called slip power recovery. You're recovering the slip power, not letting it dissipate the rotor. There is another very interesting application of this slip power recovery. Actually, those kind of solutions are again coming up nowadays. Is that for synchronous machine, what we need is a wound field synchronous machine, not permanent magnet synchronous machine. What we need is a DC power supply in the rotor. Right, now you can do it through slip ring brush gear, because you need DC on both the sides, both static and rotating. That's why it's slip ring, not commutator. Commutator has DC at one side, AC on the other side. So slip ring brush, DC power goes to the rotor. So now here you have a moving contact. Sometimes you might want to avoid that. So to do that, what is done is a hollow shaft is used. Say this is the shaft. The shaft, and this is the rotor of the synchronous motor. And here on the same shaft, the rotor of one induction motor is there. And it's a wound rotor induction motor. So it has 3 windings. Wound rotor induction motor. Now the shaft is hollow. In the shaft itself, there is a rectifier. So this rectifier is placed inside the shaft. It is rotating with the shaft. It gets power from this induction motor rotor and sends it to the DC field of the synchronous motor rotor. So you do not need any rotating contact. The rectifier itself is in the shaft, and it's rotating with the shaft. It's a very interesting concept. Okay, that's all from my side today. If you have anything else to ask, you can ask, or else I will wait for some more time and then we'll stop this session.
So this sleep power recovery and this feeding back through a motor to the rectifier, they are really practically they are used.
Yes, yes. There is something I think I forgot. Sharbia's drive. Sharbia's drive. I have forgotten that. That's why I did not want to mention the name. Yes, you search for this. I'm writing the name. SCHERBIUS. Sharbia's drive. You see what this is? This is this, not this. Because otherwise you will have lot of energy loss unnecessarily in the rotor. Why do that? Give that power back to the grid.
I'm just asking for the curiosity, sir. Suppose I am very large inductor.
Hmm.
When it's creating a magnetic, it's a coil, it's creating a magnetic field. But some fault occurs means I have to ramp down that current to zero. And suppose it's having some megajoule of energy into that.
Hmm.
So how can I recover back it some useful purpose? So we are allowing that to dump in a resistor and it heats up the resistor and it goes as a waste.
You're asking for any general situation?
Yeah,
It
like a very
depends
high
on
inductor is there.
it depends on what circuits you have. See, inductor is nothing but a current source.
Yeah,
So ideally, what you should have is a circuit breaker in parallel with the inductor. If some fault happens, this circuit breaker should close. If some fault happens, this circuit breaker should close. In this way, what is happening is your circuit is saved. Got my point? The stored energy is not suddenly released. Your circuit is saved. Now, if some fault happens, then you want to give that energy back. That may require some other extra circuitry. I don't know of any standard circuit for that.
like it's a decaying current in a LR circuit. So how can I use that? Where can I use?
What kind of circuit you are talking about?
Now, let me explain this. There is an inductor I have charged it to some high current like 10 kilo ampere
Mm.
and it's a 1 Henry cell.
Mm.
Now and it is a superconducting machine. Okay.
Okay.
Now there is a quench or something fault occurs in the coil. Now I want to because the coil cannot withstand a few seconds after the quench, and I have to ramp it down to zero. So I'm connecting a resistor and there is very high value, that is 72 milliohm, something like that. In 15 seconds is ramped down to zero.
Mm.
Now I want to use this somewhere. It's just going a waste in the resistor. It's heating up the resistor. There's
So
72 milliamp.
is there a switch? Is there a
Yeah, it
switch
is. There
that
is a switch. There is a DCCV circuit breaker. Yeah,
so
like that. And it connects when there is fault. It connects the dump resistor.
See, what I feel is you're talking about some industrial problem. Um, there is a lot of difference between what we do in reality, what we do in theory, and what is feasible in industry. But inductor was carrying DC current.
Yes. It's a 1 Henry inductor and 20
DC current
ampere
it is
current it is
carrying.
carrying.
See, I'm telling you theoretically, I do not know how much practical feasibility this will have. So what you have can be drawn like this. The inductor is nothing but a current source. So if you want to feed that current source energy back to the grid, the only option you have is this. The grid. So this is one feasible option. As soon as fault occurs, this switch should close,
Yes.
or the other way around actually. Fault occurs, the control circuit to this thyristerized inverter should be started, and then the switch should be closed. Then the energy will be given back to the grid.
Like you can try parallel this inductor, na, sir, the current source. You can
Yes.
tell a resistor across it, and this
Now,
IR voltage I can feed back to this circuit.
see, you said you have inductor
Yeah.
through which some current was flowing.
Yes.
So this is equivalent to this current source. And the current will keep decreasing. But nature-wise, I am saying, what is an
Yes. Yes.
inductor? An inductor is something that stops any sudden change of current through it. This is why I told that you turn on the thyristor control first, then you close the switch. Otherwise, if you close the switch first, it may damage some of the thyristors, the high
Yes,
voltage.
sir. Yes.
Or maybe for security, I think you can keep the thyristor control circuit on throughout. That will not cause any harm. So that when there is a fault, you simply close the breaker, energy will be sent back to the grid. But again, I am telling you, I am saying all this from a theoretical point of view.
Yes, sir.
Feasibility and all needs to be checked.
Oh, okay, sir. Thanks a lot.
Yeah. Thyristerized, just a minute, I drew thyristerized though. You are talking about very high power. Yes, thyristor is the only option, although I drew thyristor from some other thought process. It's a current sourced inverter. Current sourced inverter means thyristor.
Yeah, the level of voltage and current is very high.
Then you have to go for thyristor inverter.
Parallel circuits.
I don't know what all device is available there, but at that much high voltage and current, thyristor is the only option. You may have to parallel, but thyristor parallel, I don't know.
Yeah, thyristor we can parallel. No?
Okay, it's positive temperature coefficient of resistance. Suppose I have two devices whose nature is such that with increasing temperature, two identical devices, okay, semiconductor devices whose nature is such that with increasing temperature the resistance increases.
That is good
Now,
for paralleling.
yes, so we can parallel this. But if it's the other way around, resistance reduces with increasing temperature,
Then it's danger.
then we cannot parallel them. So that way, as you said, I did not know you said. So this can be MOSFET can be paralleled. Most probably BJTs cannot be.
Yeah, all semiconductor they have positive coefficient. No? All
No,
semiconductor.
not all, not all.
Oh, except diode.
BJT has positive.
BJT I'm not used, but diode I'm sure it is negative.
BJTs can be used. Okay, then diode you cannot use.
Yes. Is there some faster method to this complex multiplication?
Complex what?
This complex multiplication, no? Actually,
These
I am
problems.
doing rectangular to polar, then I am multiplying the polar, then I am doing that.
You can directly do it in calculator. This calculator. I am using this 991 yes.
Okay, directly we can do that.
Yes.
See, I'm having some old college time that's
Actually,
so
I
rectangular
used
to
to use
polar,
something
then
else during my school time. This 991 yes I got for these calculations only.
because we
Here
have
you
to write
can
this R
directly,
plus JX and J into
yes,
R1 plus X.
both is possible. You can have in A plus J beta format also you can write. In R theta format also you can write whatever you want. Both are supported.
And directly multiply.
Yes, all kind of operations you can do directly. Okay, then we'll stop for today. Next Monday we will meet, and most probably I will take two classes next week. I will tell in the next class because 25th I may not take the class. I will tell it in the next class.